Imagine thousands of customers hitting the buy button on Black Friday at the exact same millisecond.
Right.
Your database is just screaming. The payment gateway is choking. I mean, under normal physical circumstances, your application should be a smoking crater.
Oh, absolutely.
Yet, for the user sitting on their couch, the screen loads instantly, the cart updates, and that little confirmation pings.
Yeah, they have no idea what's happening under the hood.
Exactly. So today, we are tearing apart the invisible engine that prevents that total system collapse. We are diving into the architecture, the data engines, and the operational logic of the Django REST Framework, or DRF.
It's quite the machine.
It really is.
Mm.
So if you are gearing up to build a highly scalable backend, or maybe you're prepping for a grueling technical architecture review, or you're just possessed by this immense curiosity about the structural integrity of the modern web, well, you are in the right place.
There is, I think, this profound shift in perspective once you stop looking at software as this self-contained magic box on your phone.
Right.
And you start seeing it for what it actually is, which is a highly combative, hyper-optimized negotiation between completely disparate machines.
Okay, let's unpack this. We have our hands on a remarkably comprehensive architectural slide deck titled Django REST APIs Demystified. And our mission here for this deep dive isn't just to read you Python syntax line by line.
Yeah, that would be terrible.
We'd put you to sleep. No, we are going straight for the underlying why and how. Before we even touch Django, we need to establish the baseline of this battlefield. What exactly is an API in the context of this high-stakes data exchange? Because, we hear the term thrown around constantly.
Constantly.
But usually it's completely divorced from its actual architectural purpose.
Yeah, it's often reduced to just how apps talk, which completely misses the brilliance of the design. Fundamentally, an API, an application programming interface, is a strict, unforgiving mathematical contract.
A contract.
It is the boundary line. You have to remember that two different software systems fundamentally do not trust each other.
Oh, at all.
Right. Nor do they understand each other's internal architecture. An iOS application written in Swift has absolutely no concept of how a Linux-based PostgreSQL database indexes its tables.
Right, because if your mobile app had direct access to the database, one bad line of client-side code could accidentally drop your entire user table.
Exactly. It's an abstraction layer built on paranoia and efficiency.
Mm.
Now, the source diagram we're looking at maps out this modern API architecture landscape, and it shows a very distinct flow.
Walk us through that flow.
So on the far left, you have your back-end systems, the heavy legacy servers, the raw data lakes. Those feed into the APIs, which the deck categorizes into three specific tiers.
Right, private, public, and partner.
Yes.
Let's contextualize those tiers for you, because the distinction changes the entire security posture of your engineering team.
It really does.
Private APIs are strictly internal, right? That's your own microservices talking to each other behind a massive corporate firewall.
Yeah, total internal control.
But public APIs, that's the Wild West. You're offering developers across the globe programmatic access to your platform, like the Stripe API or Twilio.
Right, you have zero control over who's hitting those endpoints.
Exactly. But then you have partner APIs, and these act as this sort of demilitarized zone between two corporate networks.
And what's fascinating there is how that partner tier creates complex legal and technical bottlenecks. Like if you are a global airline and you open a partner API to a specific travel aggregator, you're building a highly customized, rate-limited tunnel specifically for their IP addresses.
Right, so it's not open to the public, but it's not internal either.
Right. It's literally a B2B handshake encoded in HTTP. But regardless of the tier, the diagram shows it cannot just flow directly to the end user. It has to pass through an API management system.
Before it ever reaches the mobile apps or the IoT devices.
Exactly.
I used to think of that API management layer like a maitre d' at a fancy restaurant, just checking reservations.
That's a common analogy, yeah.
But looking at the sheer volume of modern web traffic in these sources, that's entirely too passive. It's more like air traffic control trying to manage a swarm of rogue autonomous drones.
That is a much more accurate visualization, honestly. The API management system isn't just checking ID. It's executing aggressive rate limiting. It's dropping malicious payload.
It's eliminating SSL connection.
Yes, and load balancing across hundreds of servers before your Django application even knows a request exists. It is the shield wall.
But once a request gets through that shield wall, It has to communicate. And this brings us to the protocol matrix in our source deck.
Right.
It breaks down three major competing protocols for this communication: GraphQL, gRPC, and REST. We really need to dissect these.
Because picking the wrong one at the start of a project will haunt an engineering team for years.
Totally. Let's start with the alternatives to REST. The deck highlights GraphQL, defining it by its single endpoint architecture.
Yeah, so the core problem GraphQL was built to solve is what we call overfetching and underfetching.
Which is a massive problem on mobile networks. Like if I'm building a dashboard and I just need the user's first name and their profile picture.
A standard REST endpoint might send you a massive 5 MB JSON file.
Right. Containing their entire purchase history, their shipping address, account settings. That's overfetching. It's draining your data plan and your battery just to parse a giant text file I'm going to throw away.
Exactly. So GraphQL shifts the power entirely to the client. The client sends a highly specific query that says, I want the first name and I want the avatar URL. Do not send me a single byte of anything else.
And the server complies?
It does. It is incredibly efficient for front-end developers. Then, on the complete opposite end of the spectrum, the deck lists gRPC.
Which uses high-performance protocol buffers.
Yes, gRPC completely discards human-readable text. It doesn't use JSON at all. It uses a highly compressed, strictly typed binary format.
So it's basically unreadable to a human.
Completely unreadable. But it's blindingly fast. The slide notes it allows for bidirectional streaming. That means the client and server keep a persistent socket open and just blast binary frames at each other continuously.
Oh, wow.
Yeah, it is the absolute gold standard for internal microservices where, milliseconds of latency cost millions of dollars.
Okay, stop right there. I have to push back on this.
Go for it.
If GraphQL solves the mobile bandwidth problem by preventing overfetching, and gRPC is this lightning-fast binary rocket ship for the backend, why are we even talking about REST?
That's the million-dollar question.
Right. I mean, REST sends bloated text files. It has strict, rigid endpoints. Why is this entire source deck and, the vast majority of the public web still completely reliant on REST architecture? It sounds obsolete.
It really is the defining question of modern web architecture. And the answer is embedded right there in the REST column of the protocol matrix. It isn't about raw speed.
What is it about, then?
It's about survivability at an unfathomable scale. The slide highlights two things: standard HTTP methods and statelessness. Let's tackle statelessness first.
Yes, let's really dig into the mechanics of that, because stateless sounds like this abstract philosophy. But on a server rack, it means something intensely physical.
Absolutely. If we connect this to the bigger picture of infrastructure, a stateful server is a doomed server.
How so?
Well, if an architecture is stateful, it means the server has to keep a dedicated block of RAM allocated to remember who you are between requests. It opens a session.
Right, like remembering you're logged in.
Yeah. Now, if you have 10 users, fine. If you have 10 million concurrent users hitting your servers during a Super Bowl ad, your servers will instantly exhaust all their available memory just trying to remember who everyone is.
And the entire system crashes.
Yes, a completely self-inflicted wound.
So REST forces deliberate amnesia.
That's a great way to put it. It is entirely stateless. Every single HTTP request that comes from your phone to a REST API must contain all the context necessary to process it.
It has to say, I'm user 1233, here is my cryptographic token proving it, and I want to view my cart.
Exactly. The server parses the token, pulls the cart, sends it back, and instantly destroys any memory of the interaction.
Which means if I send a second request 5 seconds later, it could be routed to a completely different server in a completely different data center.
And it wouldn't matter at all. That second server can fulfill the request just as easily. You don't have to worry about sticky sessions or routing a user back to the specific server that remembers them.
You just throw more metal at the problem.
Right. You just spin up 10,000 identical servers and let the load balancer spray the traffic randomly.
That is the genius of REST. It scales horizontally with almost zero friction.
And the other reason for its dominance is its reliance on standard HTTP methods. Every load balancer, every firewall, every caching proxy in the world already understands HTTP.
Which transitions us from the landscape to the language itself.
Yeah.
Section 2 of our deep dive, the grammar of the web, the REST anatomy, and HTTP verbs.
Because we can't just throw raw text at a server. We have to use specific standardized action verbs.
Right. We are essentially manipulating resources using a highly constrained vocabulary. The source slide lists the 5 primary HTTP verbs: post, get, put, patch, and delete.
But to truly understand how these work in an enterprise environment, we have to look past the basic definitions and look at how they actually impact the database layer.
Right, because any junior developer knows get means read and post means create.
Sure.
But the architectural nightmare usually starts when developers misunderstand idempotency.
Yeah.
Let's explore that, because the difference between a posted and a PUT request isn't just semantic.
No, it's the difference between a clean database and a corrupted one.
Exactly. So what is idempotency?
Idempotency is a mathematical concept that is absolutely critical in REST API design. An operation is idempotent if you can perform it once, or you can perform it 1,000 times, and the end result on the server is exactly the same.
Okay, let's look at the GT request.
Right. If you send a GET request to read a movie profile, you can send that request 1,000,000 times. You aren't changing the database.
So it is inherently idempotent.
Yes. But the source stick defines POST as create, submits a new resource payload. Post is notoriously not idempotent.
And that is where the danger lies. Imagine a mobile banking app. You initiate a transfer of $100. The app sends a POST request to the API.
The API receives it, creates the transfer in the database, and tries to send a success message back to your phone.
But right at that millisecond, you drive through a tunnel and lose cell service.
Happens all the time.
Your phone never gets the success message. So the app panics. It assumes the request failed. When you drive out of the tunnel, the app automatically retries and sends the exact same POST request again.
Exactly, because post means create a new resource.
Yep.
The server receives the second request and creates a second transfer of $100.
Ouch.
Yeah, you just lost $200 because the client retried a non-idempotent request.
So how does PUT solve this? Because the slide defines PUT as update full, replaces an entire existing resource representation.
PUT is strictly idempotent. If you send a PUT request saying, update user 42's email to john@example.com, you can send that request 500 times.
The end state is always just going to be user 42 having that specific email.
Right. It replaces the entity at that specific URL. However, the slide explicitly notes that PUT is a full update. This is a massive trap for front-end developers.
Let's say I'm updating my profile and I just want to change my time zone. I send a PUT request with a JSON payload that just says time zone at EST. What does the API do?
If the API is strictly adhering to the REST standard, it will take that payload and overwrite the entire database record for your user.
Wait, what?
It will see that you didn't include a first name, a last name, or an email in your payload, and will overwrite those fields with null values.
So that systematically erases my identity, leaving only a time zone.
Yes, it expects the full representation.
That is absolutely lethal. It requires the client to perfectly track and retransmit the entire state of the object just to change one Boolean flag.
And that is exactly why the PAT-TCH verb was introduced.
The source defines PAT-TCH as update partial, modifies specific fields without touching the rest.
It is a surgical strike. If you send timezone EST via a PAT-TCH request, the API will retrieve the user, isolate the time zone column, update it, and leave everything else perfectly intact.
But implementing PAT-TCH on the back end is notoriously complex, right?
Sorry.
Because you have to write logic that dynamically checks every single incoming field to see if it was included in the payload.
Yeah, and then construct a highly specific SQL query on the fly to only update those exact columns. It requires immense boilerplate code if you're writing it from scratch.
Which is exactly why we are discussing the Django REST framework today. It handles that dynamic field parsing automatically.
Yes, it does.
But before we get to the framework, we have to look at the other side of this HTTP conversation, the response vocabulary. When the API finishes its database operation, how does it signal the outcome back to the client?
The source material groups these into families by the hundreds, the 200s, the 300s, the 400s, and the 500s.
And frankly, we don't need to read the dictionary definition of a 404 not found. I mean, everyone who has used the internet knows what that means.
Right, ain't missing.
Let's look at this from a DevOps perspective. When an engineering team is monitoring their API metrics, the distinction between a 400-level error and a 500-level error dictates entirely different crisis responses.
It is the ultimate allocation of blame. The slide categorizes the 400 family as client error. This means the API is functioning perfectly, the servers are healthy, but the app on your phone just sent an invalid, malformed, or unauthenticated request.
So if I see a massive spike in 400 bad request errors on my dashboard, I'm not waking up my back-end database engineers. I'm calling the iOS or Android team because they just pushed an app update with a bug that's sending garbage JSON payloads.
Precisely. The 400s mean fix your request and try again. The 500 family categorized as server error, is the exact opposite.
A 500 internal server error means the client did everything right. They sent a perfect, mathematically sound request.
And the server completely failed to process it. A database connection dropped. A Python script threw an unhandled exception. The hard drive is full.
That's when the pagers go off at 3 a.m.
Yes. But within that 400 family, the source explicitly highlights a distinction that causes constant architectural headaches. 401 unauthorized versus 403 forbidden.
They sound synonymous.
They do, but technically, they represent two completely different phases of the security pipeline.
Let's break that down for you. 401 unauthorized, according to the slide, means needs login.
It is purely about authentication. The API is saying, I have no idea who you are. You did not provide a valid JSON web token or session ID. Prove your identity, and I will let you through the front door.
So 401 is an identity failure. But 403 forbidden is defined as lacks permission.
This is an authorization failure. If the API returns a 403, it is saying, I have verified your cryptographic token. I know your name. I know your user ID. You are fully authenticated.
But you, specifically, are a standard user trying to access an administrator dashboard.
Exactly. You do not have the clearance.
And getting those two mixed up can lead to massive security vulnerabilities. If you return a 401 instead of a 403, a malicious actor might assume they just need to find a way to fake a login, rather than realizing the endpoint is structurally locked down based on role-based access control.
It is the difference between bouncing someone at the club door versus kicking out a VIP who tried to walk into the manager's office. You must send the correct signal.
Which brings us directly to how we actually build this intelligence. We've defined the landscape, we know the HTTP grammar, the idempotency traps, the status code psychology. Now we dive into section 3, the DRF ecosystem blueprint.
Let's do it.
How does the Django REST framework actually organize its internal factory floor to process these complex GTE and POST requests and spit out secure, validated responses?
To understand DRF, you have to visualize it as a highly synchronized assembly line. The source provides a blueprint diagram detailing 5 interconnected pillars.
What are they?
Writers, views and view sets, auth and permissions, serializers, and content negotiation. Let's trace how a raw HTTP request moves through this factory.
Okay, so the moment the request hits the server, it encounters the routers. The slide defines their job as automated URL mapping. But it's more than just a switchboard, isn't it? It's parsing the URL string to extract variables before it even knows what the resource is.
Yes, the router is looking at a URL like a P1 customer's 8472 orders and mathematically deconstructing it.
It identifies that the client is looking for the order's resource nested under a specific customer ID.
Right. It packages those variables and hands the entire HTTP request off to the actual brain of the operation, the views and view sets.
The blueprint labels the views as the request routers, which handle the HTTP verbs. This is where the code looks at the request and says, okay, this is a GE request. That means I need to query the database, not write to it.
But the view cannot act immediately. This is where the framework's middleware architecture shines. Before the view is allowed to execute a single line of business logic or touch the database, the request is intercepted by the auth and permissions layer.
The bouncers at the door of the view.
Exactly. The blueprint notes this layer is responsible for guarding the endpoints. It runs the request through a gauntlet of classes.
First, the authentication classes strip the headers to find the token, validating the signature to identify the user,
which prevents the 401 error. Then it passes the user object to the permission classes, which check against your business rules to see if this specific user is allowed to read this specific data,
which prevents the 403 error. Okay, so the router mapped the path, the auth layer verified the identity and the clearance. Now the view is cleared to execute. It pulls a massive, complex Python object out of the PostgreSQL database.
But the mobile app waiting for a response doesn't understand Python objects or SQL joins.
Right. It needs JSON text.
This is where we reach the most critical juncture in the entire framework, the serializers. The blueprint calls the serializer the data bridge.
Because it's translating.
Yes. It is responsible for the incredibly computationally expensive task of translating relational database rows into nested JSON strings, or vice versa. The view hands the raw data to the serializer grinds through it, and returns a clean Python dictionary.
But the slide shows one final step before the response is sent over the wire: content negotiation.
This is an often overlooked feature of DRF. The framework actually inspects the HTTP except headers sent by the client.
Wait, it checks what the client actually wants.
Yeah. The client might say, I strongly prefer JSON, but I will accept XML if that's all you have. The content negotiation layer looks at what the API is configured to output,
Yeah.
looks at what the client wants, mathematically weights the preferences, and dynamically formats the outgoing data into the perfect format.
It's an incredibly robust pipeline.
Yeah.
And the reason we rely on frameworks like DRF instead of writing this from scratch is precisely because of all these edge
Oh,
cases.
totally.
I mean, you could write a raw Python script to query a database and print a JSON string, but managing the routing rejects, the cryptographic token validation, the permission object level checks, and the content negotiation waiting.
Doing that manually for every single endpoint is how you introduce catastrophic security flaws.
Exactly. DRF gives you a battle-tested, secure slot for every single component. But the component that requires the most engineering brainpower, the component where you will spend 80% of your time, is the serializer,
No question.
which takes us deep into Section 4, the translation layer, the serializer engine. If the view is the brain of the API, the serializer is the heart. It pumps the lifeblood, the data in and out of the system.
The source deck provides a dedicated slide titled The Data Engine, Serialization, and it breaks down the exact mechanics of this two-way translation process.
Here's where it gets really interesting, because a serializer isn't just a formatting tool. It is a dual-engine protocol translator. The slide details two core methods that power this engine: tool representation and tool internal value.
Let's walk through the exact memory transformation that happens here.
Let's look at tool representation first. This is the outbound engine, right?
Yes, you have executed a database query, and you now have a complex Django model instance in server RAM. This model has datetime objects, UEDs, relational foreign keys, and decimal types.
And you cannot just send a Python datetime object over the internet.
No, it has to be a string. When the view calls to a representation, the serializer recursively iterates over every single field in that model.
It converts the date times into ISO 8601 formatted strings. It converts decimals to string floats to prevent precision loss.
Right. It flattens the complex object into a clean, primitive Python dictionary, which is then finally passed to a JSON renderer.
That handles GET requests perfectly. Database to JSON. But what about the inbound traffic? The PST and PUT requests.
That triggers tool internal value. This is significantly more dangerous because you are accepting raw text from an untrusted source across the internet.
Right, you have no idea what they're sending.
The serializer takes the incoming JSON payload, parses it into a dictionary, and then runs it through a gauntlet of typecasting. It takes a string that looks like a date and tries to instantiate a true Python datetime object.
It takes an integer and verifies it can be safely cast.
If any of this fails, it instantly halts and prepares an error response. Only if it succeeds does it return validated Python data ready to be saved.
Now, DRF gives developers 3 different ways to build these engines, which the source calls serializer archetypes. You have to choose how much automation you want versus how much raw control you need. The 3 archetypes are serializer, model serializer, and base serializer.
The base serializer class is what the slide calls the manual blueprint. It forces you to be explicit.
Meaning you have to write out every single field definition, like email, serializers.emailfield.age, serializers.integerfield.
Yes. You are manually declaring the exact structure of the data payload. Furthermore, you have to write your own create and update methods to tell the framework exactly how to insert that data into your database.
It's verbose, but it gives you total granular control.
It does.
But the reality is 90% of the time, your API payload looks exactly like your database table. If my database has an email column and an age column, writing a manual serializer feels like violating the DRY principle. Don't repeat yourself.
Which is why the model serializer was invented. The slide calls it the automated engine.
How does it automate it?
Instead of redefining every field, you give the serializer a meta class and simply point it at your Django database model. DRF uses introspection.
It looks at the database schema.
Exactly. It sees that email is an email field in the database and automatically generates an email field in the serializer. It dynamically builds the entire translation engine on the fly, and brilliantly, it automatically implements the create and update logic for you.
It is absolute magic when it works. You can spin up an endpoint in 5 minutes. But I want to talk about the third archetype, the base serializer, which the slide calls the custom override. Because model serializer is great until it suddenly isn't.
When the magic fails, it fails hard.
So when do we use base serializer?
If we connect this to the bigger picture of enterprise integration, the model serializer assumes a one-to-one mapping between your API and your database. But what if you are building a modern mobile app? and your backend is actually communicating with a 30-year-old mainframe running a legacy banking system.
Oh, wow.
The mainframe doesn't speak REST. It spits out fixed width, EBCDIC encoded text strings.
A completely alien format.
Exactly. You cannot use a model serializer for that. You have to inherit from base serializer. You have to completely override the Tor representation and internal value methods.
You write raw Python code that manually opens a socket to the mainframe, pulls the fixed width string, mathematically parses it byte by byte.
Constructs a JSON payload by hand, and sends it out. Yes, you use base serializer when you need to bypass all the automation and build a highly bespoke, specialized data bridge.
That sounds like a nightmare, but it's crucial that the framework provides that escape hatch. Now, even if you stay within the happy path of the model serializer, the source material highlights advanced serializer mechanics, because even automated engines need fine-tuning.
Let's look at 3 powerful tools: source, depth, and extra quick works.
Let's start with source. This is an incredibly elegant way to decouple your database schema from your public API contract. The slide notes it's used for renaming fields in transit.
Give me an example.
Okay, let's say your database administrator 10 years ago named a column osract VLAG's Boolean. It's a terrible name. Your front-end React developer refuses to use it in their code. They want the JSON field to just be called isActive.
Naturally, you don't have to migrate your entire production database to fix the name. In your serializer, you define a field called isActive, and you set the parameter source osract VSLG Boolean.
So when DRF serializes the data, it reaches into the database, grabs the horribly named column, but outputs it in the JSON under the clean, modern name.
The front end gets what they want, the database stays untouched, and the mapping happens silently in memory.
That's brilliant. Now let's talk about the depth parameter. The slide says, setting depth equals 1 auto-expands relational IDs into fully nested data structures.
This sounds incredibly convenient.
It does, but I have to raise a massive red flag here. If I'm querying a list of 50 orders, and each order has a foreign key to a customer, if I just output the customer ID, that's one database query for the orders. But if I set depth 1, isn't DRF going to query the database again for every single customer?
Yes. Yes, it is.
Doesn't this create a catastrophic n+1 query problem?
This raises an important question about the hidden costs of abstraction. Yes, you're absolutely right. If you blindly set depth 1 on a list endpoint, DRF will execute one query to get the 50 orders and then loop through them, executing 50 separate SQL queries to fetch each individual customer profile.
It will completely hammer your database and spike your latency.
So how to use it safely?
You must pair the serializer's depth parameter with highly optimized database queries in your view. You have to use Django's select-related or prefetch-related methods,
Which forces the database to execute a massive SQL join operation up front, pulling all the orders and all the customers into memory in a single query.
Then, when the serializer with depth 1 runs, it already has the data cached in RAM and doesn't need to hit the database again. The depth parameter is powerful, but it requires deep operational awareness.
Okay, let's look at the third mechanic, extra quawks. I want to build a scenario around this because it touches on critical data compliance, things like GDPR or right to pay.
Let's say we have a user model. It has an email, a birth date, and a highly sensitive password hash. The mobile app needs to be able to send the password during account creation, which is a POST request.
Right.
But under absolutely no circumstances should that password hash ever be exposed in a GET request. How do we build a one-way street?
You use extra quirks to inject silent constraints into the automated model serializer. In the meta class, you define extra quirks
Rhino.
write only.
Yes.
That single Boolean flag fundamentally alters the behavior of the translation engine. When Tor internal value runs on an incoming POST request, it accepts the password, validates it, and saves it to the database.
But when Tor representation runs to generate the JSON for the response?
The engine sees the write-only flag and actively strips the password field out of the payload before it ever hits the network interface.
You secure PII and cryptographic secrets with a single line of code without having to manually construct the entire field dictionary.
Now, speaking of these complex data structures, the final slide in this section is the relational fields diagnostic. It details how a serializer handles relationships between different models. Because an API is rarely just flat tables, it's a web of connected resources.
The source uses a movie and a streaming platform as an example.
Handling relationships is notoriously tricky in REST because you are trying to represent a multidimensional graph in a flat text file.
The slide outlines 4 distinct representations. The first is primary key related field. This is the absolute leanest approach. The JSON simply outputs platform 1. It returns the raw numeric ID.
Which is perfect for a mobile app that already has a local SQLite database catching all the platform names.
Yeah.
It just needs the integer to make the connection locally.
It minimizes the payload size to save bandwidth. But if I'm building a public data API that researchers are querying via the terminal, the number 1 is entirely opaque.
For that, you use the string-related field. The output becomes platform, Netflix. The serializer dynamically calls the Python _stream method on the related model to generate a human-readable name.
The slide notes, it is best for immediate human readability, but crucially, it is read-only. You cannot submit a post request with the string Netflix and expect it to automatically find the ID.
What if I do want the user to be able to submit a string? What if my front end has a drop-down menu of text names and I want them to just post the name Netflix to link the movie?
Then you implement a slug-related field. You configure the serializer to look up the relation based on a specific, unique string column, a slug. The output is platform, Netflix, but unlike the string field, it is fully read-write capable.
The toy internal value engine takes the string Netflix, queries the database for a platform with that exact name, retrieves its ID, and establishes the foreign key relationship automatically.
And then we reach the final option, which is arguably the purest expression of REST architecture, the hyperlinked related field.
The output here completely abandons IDs and names. It looks like platform, https://api.example.com/v1 platforms1. It embeds a fully qualified navigable URL directly into the JSON.
This touches on a concept called Hadeos hypermedia as the engine of application state. The idea that a client shouldn't need a hard-coded manual to understand your API.
It should be able to dynamically crawl it just by following the links provided in the payloads, exactly like a human browsing Wikipedia.
The slide notes, this is best for API discoverability. It is architecturally beautiful. But in practice, many front-end engineering teams despise it because parsing strings to extract IDs from URLs is tedious, and they would rather just have the integer.
It is a constant architectural tug-of-war between back-end purity and front-end pragmatism.
It is. But before any data, whether it's an ID, a slug, or a URL, can be saved to the database, it has to survive the gatekeepers. Translating data is useless if you are translating malicious SQL injection attacks or corrupted payloads.
This brings us to Section 5, the bouncer at the door, the validation pipeline.
Data integrity is the difference between a functional application and a compromised enterprise. The source deck visualizes this as a strict sequential pipeline triggered by a single command in the view. Serializer is valid.
The moment the command fires, a 3-step lockdown process begins. Walk us through Step 1.
Step 1 is ingestion. This is the foundational sanity check. The framework looks at the incoming HTTP body. Is it actually formatted as valid JSON, or is it a garbled string of hexadecimal bytes?
Do they send an array when we expected a dictionary?
Right. If the core structure is malformed, it fails immediately before any complex logic runs.
Assuming it is clean, structured JSON, we move to Step 2, field-level validation.
This is a highly granular inspection. The framework looks at every single piece of data in isolation. The slide shows the syntax validate field name. For example, if your serializer has a field called discount code, DRF will automatically execute a method called validate discount code if you've written one.
So in this method, I could write a regex pattern to ensure the discount code is exactly 8 alphanumeric characters, completely capitalized.
It doesn't care about anything else in the payload. It is only
Right.
looking at that specific string in a vacuum.
It checks if the age is a positive integer. It checks if the email contains an @ symbol. But validating fields in a vacuum is rarely enough for complex business logic.
Which brings us to Step 3, object-level validation, utilizing the overarching validate method.
The slide explicitly states this step has access to all fields simultaneously.
I want to build a complex business scenario to illustrate why this is mandatory. Let's say we have an e-commerce API. The payload contains requested quantity. Let's say they want 50 laptops, and user tier, they are a standard user.
Perfect example. During Step 2, the field-level validation looks at requested quantity. Is 50 a valid integer? Yes, it passes it. It looks at user tier. Is standard a valid string? Yes, it passes.
But our business logic dictates that standard users are hard-capped at buying 10 items per order to prevent inventory hoarding. Only wholesale users can buy 50.
You cannot possibly enforce that rule in Step 2. When the validate requested quantity method is running, it is entirely blind to the user tier. They are evaluated in separate memory spaces.
Step 3, the object-level validate method takes the entire dictionary of clean data and evaluates the relationships between the fields.
Here you write the logic. If usertier is standard and the requested quantity is greater than 10, raise a validation error.
You are enforcing the cross-field dependency. Now, what actually happens when the bouncer rejects a payload? Let's tie this back to the HTTP grammar we discussed earlier.
The pipeline halts instantly. The framework throws the serializers. Validation error. The view catches this internal Python exception, aborts the database transaction, and automatically constructs a clean HTTP response.
And because this was a failure on the client's part, they submitted invalid data, it returns a 400 bad request status code.
Brilliantly, DRF includes a JSON payload in that 400 response, detailing exactly which field failed and why, so the front-end app can display a red error message under the specific input box.
And if it passes all 3 steps?
The data is deemed valid. DRF populates a secure dictionary called validated data. The view is now cleared to call serializer.save, which executes the database commit and returns a 200-level success code.
Okay, so we've spent a massive amount of time on the serializer and its bouncers. We know how data is translated, verified, and secured. But what is actually orchestrating all of this?
What receives the signal from the router and tells the serializer to get to work?
This brings us to section 6, the control room, the view architecture pyramid.
The view is where your HTTP request physically collides with your application's logic. And DRF approaches views through a paradigm of increasing abstraction, which the slide visualizes as a pyramid.
At the very base of the pyramid, the foundation, we have the raw Django view.
This is the unadorned native handler. The slide notes it is the raw HTTP handler base class. If you use this, you are operating without a safety net.
You have to manually read the HTTP stream. You have to manually parse the bytes into a string. You have to handle all the error catching yourself.
It is wildly inefficient for building a modern REST API.
So we step up to the first tier of the framework, the DRF API view.
This is where the magic begins. The slide explains that API view replaces standard requests with DRF request objects.
This is a massive architectural upgrade. DRF intercepts the raw incoming stream, parses the JSON, and hands you a clean, intelligent request.data object.
It also wraps your code in a massive try-except block, handling content negotiation and API exceptions. If your database connection drops in the middle of a query, the API view catches the crash and gracefully returns a 500 internal server error formatted in JSON.
Rather than vomiting a raw Python trace back to the client. But inside an API view, I still have to write the manual logic. I have to say if request.method equals GET, do this query, instantiate this serializer, return this response. It's still a lot of boilerplate.
Which leads us to the next massive leap in abstraction, the generic API view.
Now we are entering the realm of automation. The generic API view is the workhorse of DRF. The source provides a dedicated slide detailing its core attributes. It abstracts away the boilerplate by asking you to define just a few key variables.
You provide a query set, for example, movie.objects.all. This tells the view what data pool it operates on. You provide a serializer class, telling it which translation engine to use.
And you define a lookup field. The slide notes it defaults to PK primary key but can be overridden. This is how the view knows how to pluck a specific object out of the URL string, right?
Exactly. If your URL is movies1, the default PK lookup field works perfectly. It looks for the ID 1. But if you want SEO-friendly URLs like Movies Inception, you override the lookup field to be title or slug.
The generic API view automatically rewrites its internal database queries to search by that specific column.
But wait, a generic API view has the data, and it has the serializer, but it still doesn't inherently know what to do with them. It doesn't know if it's supposed to list them, create a new one, or delete one.
And that takes us to the absolute peak of the pyramid. Concrete views, the slide lists examples like list create API view. These are ready-to-use endpoints combining mixins.
I want to spend some time on this mixing concept, because Python supports multiple inheritance, which can easily devolve into an unreadable mess of spaghetti code if not handled perfectly. Why did DRF choose a mixin architecture instead of just writing massive monolithic classes?
It is a masterclass in composition over inheritance. A mixin is a small, hyper-focused packet of pre-written logic that does exactly one thing. The source provides a brilliant mixin to HTTP mapper slide. Let's trace how perfectly these align with the HTTP verbs we discussed in section 2.
Let's do it.
If you attach a list model mixin to your view, it injects a highly optimized .list method. It automatically listens for a GET request to a base URL, pulls the entire query set, serializes the array, and returns a 200 OK.
And if I attach a create model mixin?
It injects a .create method. It listens for a piece request, takes the payload, runs the full 3-step validation pipeline on the serializer, executes the database save, and returns a 201 created status.
What about operations on a specific single object?
The retrieve model mixin handles get-to requests with an ID in the URL. It fetches the object, serializes it, and returns a 200 OK. Crucially, the ID doesn't exist in the database. The mixin automatically throws a 404 not found error.
You don't have to write the try except block.
Exactly. The update model mixin handles PUT and PAT-CH requests, managing the full or partial validation logic automatically. And the destroy model mixin handles delete requests, wiping the record and returning a 204 no content.
So if I use the concrete list create AP view at the top of the pyramid, DRF is literally just taking the generic AP view base, pasting the list model mixin and create model mixin onto it, and handing me a fully functional endpoint.
I provide 2 lines of code, the query set and the serializer, and I get a secure, validated, paginated API endpoint that can list all records and create new ones. The amount of engineering time that saves is staggering.
It allows small teams to build enterprise-grade APIs in weeks instead of months.
But there is a catch. There's always a catch. Concrete views and mixins are miraculous when your business logic perfectly aligns with standard CRUD operations: create, read, update, delete.
But what happens when the default automation isn't what you need? What if you need to bend the rules of the framework?
This takes us to Section 7, hack the matrix intercepting the view lifecycle.
Every powerful framework must provide an escape hatch. If a framework is too rigid, developers will eventually abandon it. DRF provides the customization zone.
The source deck visualizes this as a timeline. A request arrives, and before the view executes its mixin logic, it runs through a series of internal hook methods: get serializer class, get query set, filter query set, and paginated query set.
By overriding these specific methods in your view, you can inject highly custom logic at the exact millisecond before the data is processed.
You are intercepting the internal machinery. Let's make this highly practical. I'm going to throw 3 high-stakes engineering scenarios at you based on the source material. You explain how we hack the matrix to solve them.
Let's hear them.
Scenario A. We are building an HR platform. We have an employee profile endpoint. When an HR admin sends a GET request, they need to see the employee's salary, their social security number, their full history. But when a regular employee queries that exact same endpoint, they should only see the public profile name, department, email.
We need the view to use a highly detailed serializer for admins and a heavily redacted serializer for regular users.
Yes.
To solve that, you intercept the getSerializer class method. The slide notes you intercept to dynamically change serializers. In your view, you write a custom function that overrides the default behavior. You inspect the request.user object.
And write the logic.
Right. If request.user.isStaff is true, return admin employee serializer. Else, return public employee serializer. The framework will execute your logic dynamically, routing the data through entirely different translation engines based on the user's role.
Closing a massive data exposure vulnerability. Brilliant. Scenario B. This is the big one. We are building a multi-tenant SaaS application, like a project management tool used by hundreds of different companies. All of their tasks are stored in the same massive database table.
If a user queries the task endpoint, the default query set is going to pull every task from the database.
Yes. And if Company A's user accidentally sees Company B's highly confidential product roadmap, our company will be sued into oblivion. We cannot rely on object-level permissions. We need to sever access at the root.
This is the most critical interception in all of DRF. You must intercept getQuerySet. The slide explicitly explains you use this to filter the raw data pool. The default attribute might be task.objects.all. You override the method to return task.objects.filter. Tenant self.request.user.tenant.
So before the view even knows what to do, before the serializer even spins up, the entire data pool is mathematically restricted to only rows belonging to that specific company.
Exactly. Even if a malicious actor tries to guess the ID of a task belonging to another company in the URL, the framework will return a 404 not found. Because as far as the filtered query set is concerned, that ID literally does not exist in the database.
It is absolute cryptographic isolation at the database query level. Okay, final scenario. Scenario C. Our application is successful. We now have 10 million records in the database. Users need to search the data. And obviously, we cannot serialize and transmit 10 million JSON objects to a mobile phone.
No, it would melt the device's RAM and crash our servers.
So what do we do?
You intercept 2 methods here to control the flow of data. First, filter query set. The source states you use this to apply third-party search or ordering backends. DRF allows you to plug in complex search engines that analyze URL parameters like search urgent ordering created and dynamically append massive SQL and order by clauses to the database query before it executes.
But the search might still return 500,000 results.
Which is why you immediately intercept a paginate query set. The slide notes this is used to chunk data payloads for massive datasets. DRF will take the massive query result, apply in SQL limit and offset, and fetch only the first 50 records.
It serializes those 50 records, and critically, it wraps the JSON response in a pagination envelope that includes a next hyperlink.
The mobile app renders the first 50, and when the user scrolls to the bottom of the screen, the app follows the next link to fetch the next 50. You preserve server memory, you preserve database CPU, and you preserve client bandwidth.
It is incredible how these intercept points allow you to fundamentally alter the physics of the framework without breaking the automated mixins. You really are hacking the matrix.
The customization zone is the sole reason DRF scales from simple weekend prototypes to massive enterprise-level financial systems.
Okay, we have reached section 8, synthesis. Bringing it all together. We have spent an immense amount of time dissecting every single atomic component of this engine. We've mapped the routing, debated the HTTP semantics, deep dived the two-way serializer engine, enforced data integrity with the bouncers, and climbed the view abstraction pyramid.
Now it is time to watch the car drive from start to finish.
Let's trace the full life cycle of a request. From the millisecond it leaves the client to the millisecond it returns. So what does this all mean? The source deck provides a final capstone diagram. Synthesis, the DRF request lifecycle. I want you to narrate this journey. Let's imagine a mobile user is checking out of an e-commerce app. They tap the place order button, follow the payload.
Let's execute the trace. Step 1. The client app constructs a JSON payload containing the cart details and payment token. It fires a post request across the cellular network.
Step 2. The payload hits the API management layer, passes rate limiting, and hits the Django server. The DRF router catches it. The router parses the URL appev1 orders and maps it directly to the order create view.
Step 3. The view takes over. Because this is a post request, the generic appev architecture delegates the task to the create model mixin. But before it executes, it hits the auth and permissions layer. It verifies the session token and confirms the user is allowed to make purchases.
The bouncers clear the VIP.
Step 4. The mixin selects the order serializer. Operating inbound, the serializer fires up the toy internal value engine. It parses the raw JSON bytes into a Python dictionary. It triggers the 3-step validation pipeline. Ingestion passes. Field-level validation ensures the quantities are positive integers. Object-level validation ensures the total price matches the sum of the items.
Everything is mathematically perfect.
Step 5. The serializer is marked valid. The view calls save. Django translates this into a highly optimized SQL insert statement, locking the database row, committing the transaction, and securing the data to the hard drive.
Step 6. The client is still waiting. The serializer immediately flips into outbound mode. It takes the newly saved database model and runs to representation. It flattens the complex order object back into a clean JSON dictionary, perhaps utilizing depth 1 to embed the shipping details, and extra forks to completely strip the credit card token from the outbound message.
A completely secure, scrubbed payload.
Step 7. The serializer hands this dictionary back to the view. The view wraps it in a formal DRF response object. The content negotiation layer verifies the client wants JSON and renders the string.
Step 8. The router dispatches the response. The mobile app receives a 201 created HTTP status code alongside the JSON confirmation data. The UI updates. The user sees a green check mark, and the stateless server immediately forgets the user ever existed, ready for the next request. Total elapsed time, roughly 45 milliseconds.
Hearing the entire orchestration laid out like that, it completely shatters the illusion of the magic box. When you tap a button and an app responds instantly, it isn't magic. It is a highly violent, incredibly strict, mathematically precise factory floor.
Millions of these exact life cycles are happening every single second across the globe, scaling horizontally to meet unimaginable demand.
And that silent, predictable orchestration is the very foundation of the modern digital economy. It truly is. If you, the listener, have made it through this entire architecture review, you should be immensely proud. We have covered a staggering amount of ground.
We debated the sheer necessity of statelessness to prevent server collapse. We exposed the idempotency traps hidden in each TTP verbs.
We tore apart the serializer engine, navigating the dangers of N+1 queries and legacy data bridging. We locked down our endpoints with object-level validation and matrix hacking query set interceptions. You now possess the underlying why and how of enterprise backend development.
Synthesizing this level of architectural density gives you an entirely new lens through which to view software engineering. But before we conclude, I want to pose a final provocative thought regarding the trajectory of this technology. Throughout this deep dive, we observed a constant drive toward higher abstraction, from manual Django views to automated mixins, from manual fields to introspective model serializers. As artificial intelligence becomes deeply integrated into our infrastructure, ask yourself, how long until the framework itself becomes fully autonomous? How long until DRF or its successor uses the customization zone to automatically profile traffic, write its own hyper-optimized serializers, and dynamically alter its own validation logic on the fly simply by observing how clients fail? Will the back-end engineers of tomorrow actually write API endpoints, or will they merely set the architectural boundary constraints while the framework constantly rewrites itself to achieve perfect efficiency?
Now, that is an incredible paradigm shift, moving from building the engine to merely managing the factory that builds the engine. Fascinating. Thank you for joining us on this exhaustive deep dive into the invisible machinery of the web. Keep asking questions, keep pulling back the curtain on how these massive systems operate under extreme pressure, and the next time you tap a button on your phone and expect that self-contained little universe to respond. Take a second to appreciate the chaotic, highly orchestrated web of routers, serializers, and bouncers working tirelessly in the dark just to bring you that data. Goodbye for now.